In the previous videos, we have found the position x as a function of time. This is equation 6. We have also found the position y as a function of time, t. From these two equations, we can find the trajectory of the projectile with air resistance. To find the trajectory from equation 6, the equation 6 is x equal v0 I'm divided by b cosine theta times bracket 1 minus e to the power minus b divided by m t. This is equation 6. Now, from equation 6, we can find the whole bracket 1 minus e to the power b divided by m t bracket equal x divided by v0 times m divided by b cosine theta. This equation we needed later on. From this equation, we can find further e to the minus b divided by m t equal 1 minus x divided by v0 times m divided by b times cosine theta. And further, we can write down here, if I take logarithm on both sides, we have minus b divided by m t log e, and this equal to 1. And on the right side, we have log 1 minus x divided by v0 I'm divided by b times cosine theta. And the time t we can write minus I'm divided by b L n minus x v0 I'm divided by b cosine theta. bracket. And this equation we also need. Now, we can substitute this equation and this equation to the previous one, position y as function of time. So this one, this has t. This one, t, we can substitute this t into here, and this whole term in the bracket we can substitute here. So we get the following. So y equal minus I'm divided by b g t plus bracket I'm square b square g plus I'm divided by b v0 sine theta, and here one minus so we do the following. This term we plug in here. This term we plug in here, and this one we plug in here. So we get y equal g minus ln 1 minus x v0 I'm divided by b cosine theta bracket on a square bracket. So we plug in this expression into here, so we get here. Then plus I'm square b square times g plus I'm b v0 sine theta x divided by v0 I'm divided by b cosine theta. And we can simplify this equation as I'm square b square g log 1 minus x v0 I'm b cosine theta plus I'm b g 1 divided by v0 cosine theta plus tangent theta x. We can reorganize this expression as the following. Tangent theta plus I'm g b v0 cosine theta x plus I'm square g b square log 1 minus bx I'm v0 cosine theta bracket, and on the left side we write as y. This is the trajectory equation for the projectile with air resistance. So this equation only contains y as function of x here, x here, x here, and time, the variable is gone. And we demand that this argument should be bigger than 0. 1 minus bx I'm v0 cosine theta greater than 0. So the argument logarithm greater than 0. If I reorganize this, I can simplify as 1 greater than bx I'm v0 cosine theta. That is x must be smaller than I'm v0 cosine theta divided by b. So this is the x range. As time approaches infinite, the x is close to this value. When you plot the trajectory y as function of x, the x range must be smaller than this quantity, m v0 times cosine theta divided by b. Otherwise, logarithm you get imaginary number. Now we have the trajectory y as function of x for the case with air resistance. Now, what happens if b approaches 0? In that case, when b approaches 0, this equation should reduce to the trajectory without air resistance. So we can prove that when b approaches 0, this trajectory equation will reduce to the trajectory equation without air resistance. Now we prove that. Now, if b approaches 0, the trajectory with air resistance will be the trajectory without air resistance. We prove this conclusion with the following. Consider logarithm 1 minus x equal minus x minus x squared minus 3x cubed. For the absolute x smaller or equal than 1. This is just a Taylor expansion of a logarithm. And you can find this expression in any mathematics textbook, or you can find from wolfram.com. When using this expression, we can have the following. Log 1 minus bx I'm v0 cosine theta equal, we only keep two leading terms. So we have here, when b is small, this whole term is b small. So we keep two terms in here expression. So we have here minus bx I'm v0 cosine theta. So we consider the whole term as x in this expression. So the first term is minus x, so minus this whole term, so bx divided by I'm v0 cosine theta. Then minus the second term. On the bottom we have 2. On the top we have bx I'm v0 cosine theta bracket square. We only need two terms. The right term, even we keep it, it will be 0. So for here we have logarithm this expression, then we substitute this expression to here, to the trajectory equation here. We substitute logarithm of this expression here. So we have y equal tangent theta plus mg bv0 cosine theta x plus m square g b square. We have bracket. So this term we use here. So minus bx I'm v0 cosine theta minus two bx I'm v0 cosine theta bracket square. Now we can simplify this equation as here. The first term tangent theta times x plus I'm gx bv0 cosine theta minus I'm square g b square bx I'm v0 cosine theta minus I'm square g b square 2 bx I'm v0 cosine theta square. Now this term and this term, they cancel each other. So this term and this term go to 0. So we have only the following remains. Tangent theta times x minus I'm square g b square x square I'm square v0 square cosine theta square and 2. And we can simplify as the following. This one we can simplify again. So we obtain y equal tangent theta x minus g x squared 2v0 square cosine theta square. And this is the trajectory for projectile without air resistance.